Floods strike without warning, storms tear through lives uninvited, but what if we could see disaster before it even arrived? What if technology could not just respond but warn, guide, and protect? Introducing Flood Factor, an AI-powered computational platform for flood prediction, visualization, and community interaction. Hello, we're a passionate team of 5 high schoolers from Bangladesh. We are developing data-driven tool for water-related disaster prediction, response, and mitigation. Our platform has 4 main parts. Our machine learning model predicts rainfall and flood risk using historical data of 45 years pulled from the Bangladesh Water Development Authority. It factors in things like temperature, rainfall, humidity, and sunshine. We went with an XGBoost regressor scoring around 0.8 on the R-squared scale, which is a pretty solid accuracy. This setup gives early warning about rainfall intensity and flooding levels. This is the front end of a computational framework. Here user can input a location, say Feni River, Feni, Bangladesh, along with rainfall intensity like 5 inches per hour and duration such as 150 hours. Once the submit button is hit, the system starts pre-processing the flood simulation. This typically takes about a minute, so while it's running, let's dive into the code to see how this all works under the hood. The first step is geocoding the user's input. We use Team from OpenStreetMap to convert this into precise coordinate. Next, we define a bounding box around this point of 100 square kilometer area. To do this, we calculate the box's boundaries in degrees, accounting for the Earth's curvature, and convert distances like 5 kilometers in each direction in latitude and longitude offsets using the Haberstein formula. With the bounding box set, we download a digital elevation model or DEM to Open Topography and pre-process it with the white box tools library. Pre-processing is critical. It involves algorithms like bridging depression, flow accumulation, and flow direction. Using the flow accumulation data, we set a threshold to extract major stream areas where enough water accumulates to form channels. For the Feni River, this highlights the main river and its tributaries. Then we identify the pour point, which is the pixel with the highest flow accumulation, representing where water exits in the system. Using this pour point, we run a watershed delineation algorithm to map the entire drainage basin feeding into that exact point. To make our flood prediction more realistic, we use land cover data from ESA. This is a high-quality satellite data. Each land cover type gets a runoff coefficient. We calculate the mean coefficient for the watershed. Now we calculate the peak discharge. We use the rational method, which is a standard hydrological approach, which multiplies the runoff coefficient C into rainfall intensity I and watershed area A. For our example, with 5 inches per hour of rainfall and a watershed area calculated from the DEM, we compute the volume of water rushing through the pour point. If users do not provide rainfall data, our machine learning model steps in. Then flood inundation is simulated using the bathtub model. This approach treats the watershed like a bathtub, filling it with water based on the discharge and duration. The 150-hour duration input helps us model how the flood evolves over time. Finally, we visualize the result. We used Matplotlib to create a 2D flood depth map, color-coded to show water depths across watershed. For a more immersive view, you use PyVista. We use PyVista to generate an interactive 3D model of the entire floodplain. This model let users rotate and zoom to see exactly how water spreads across the whole terrain, highlighting the vulnerable areas like low-lying villages. These visuals are crucial for communicating flood risk to stakeholders and get area-specific information. Moreover, our community network keeps everyone connected during floods. People can report needs like rescues, roadblocks, or shelter updates using tags such as evacuation or safety. This real-time crowdsourced info helps rescue teams and volunteers stay on top of things, making response faster and more targeted. The statistics page will show all of the most important information from government warnings to shelter occupancy in one simple location. This will be really useful during big flood events.